And yep, I am live, and we will just straight up continue. And in the last stream, we left here. We completed this section, this shell section. And what is a shell? Shell is just a program which you can use to interact directly with the kernel. That is cool, right? You can type in commands in the terminal. The shell, you can interact with the shell through the terminal, and you don't have to go through the trouble of making system calls and stuff. You can just tell shell the commands that you want to run, and shell will interact with the kernel on your behalf and run those commands. Now, pipes, as you might know, they bring water to your house. But here, pipes are perhaps the single most striking invention in Unix. A pipe is a mechanism provided by the operating system and made easily accessible through the shell that connects the output of one program to the input of another. Standard input, standard output. The operating system makes it work. The shell notation use it notation to use it is simple and natural. The effect is a new way of thinking about how to design and use programs. The idea of connecting programs has been around for a while. One of the clearest statements in the Unix context appeared in an internal document that Doug McElroy wrote in 1964, advocating, among other things, the idea of screwing programs together like garden hose. Figure 4.1 is from a well-worn page that hung on the wall in my office at Bell Labs for 30 years. By the way, notice the typing errors and the generally terrible quality. This illustrates what typewritten documents often look like. The bottom part of the figure is corrected transcription. Summary. And shit. Well, it is not lagging, but this is due to some reason. Shit. Uh, Shit, my MacBook is lagging. That is crazy, and it is lagging while reading a PDF. That is just absolutely crazy. Summary, what's more important? To put my strongest concern in a nutshell, we should have some ways of coupling programs. Bike, like garden hose, screw, in another segment when it becomes then it becomes necessary then it becomes necessary to manage data in another way. Somebody, what's more important? To put my strongest concerns in a nutshell, we should have some ways of coupling programs like garden hose screw in another segment when it becomes necessary. When it becomes necessary to massage, massage, massage data in another way. Okay. To massage data in another way. That is what they want to say, massage. They wanted to allow arbitrary connections in a sort of mesh of programs, but it was not obvious how to describe an unconstrained graph in a natural way, and there were semantic problems as well. Data that flowed between programs would have to be queued properly, and queues could explode in an anarchic anarchic connection of programs, and Ken couldn't think of any real applications anyway. But Doug continued to nag, and Ken continued to think. As Ken says, one day I got this idea: pipes, essentially as they are today. He added pipe system call to the operating system in an hour. He describes it as super trivial given that the mechanism for I/O redirection were already there. Ken then added the pipe mechanism to the shell, tried it out, and called the result mind flowing. The pipe notation was simple and elegant. Elegant. A single character, the vertical bar between a pair of commands. So, for example, to count the number of files in a directory, um, pipe the output of ls, one line per file, into the output of wc, counts the lines. Let's go by term. David Goggins, ls, wc, and 37 files, it seems. Now, it is often appropriate to think of a program as a filter that will read data, that will read data, process it in some way, and write the output. Sometimes this is perfectly natural, as in programs that select or mutate or count things on the fly. But sometimes the filter does not operate on the fly. For example, the sort command necessarily has to read all its inputs before it can produce any output, but has to read all its input before it can produce any output. Has to read all its input before it can produce any output, but it is irrelevant. It still makes sense to package it as a filter that can fit into a pipeline. Ken and Dennis upgraded every command on the system in a single night. The major change was to read data from standard input stream when there were no input file name arguments. It was also necessary to invent standard error, the standard error stream. The standard error was a separate output stream. Error messages sent to it were separated from the standard output and thus would not be sent down a pipeline. Overall, the job was not hard. Most programs required nothing more than eliminating extraneous messages that would have cluttered a pipeline and sending error reports to standard error. The addition of pipes led to a frenzy of invention that I remember vividly. I don't have an exact date, but it would have been in the second half of 1972 when Godfather came out. Since pipes were not in the second edition of the manual in June 1972, but were present in the third February 1993. Everyone in the UNIX room had a bright idea for combining programs to do some task with existing programs rather than by writing new programs. One of mine was based on the who command, which lists the currently logged in user. A command like who isn't terribly relevant today when most people work on their own computer, but since the essence of time sharing was sharing the same computer, it was helpful to know who else was using the system at the same time. Indeed, who added to the sense of community. You could see who was also working and perhaps get help if you had a problem, even if both parties were at their homes late at night. Yup. The who command prints one line for each user in for each logged in user. Grep searches all the occurrences of a specific pattern, and WC counts the number of lines. So the pipeline report on the status of ah get the who command. Then grep Joe find the lines in which Joe appears and count. Let's see how many Joes, how many times Joe logged in, or how many Joes are there. To see what an improvement pipes were, consider how the last task would have been performed without pipes using input and output redirection to files. This put the output of who to temp 1 and then grep Joe in temp 2 and put the answer to temp 2 and put temp 2 to WC. Following followed by removing the temporary files. Pipes make this into a single command without temporary files. Ken's favorite pipe example was a speaking disk calculator that used Bob Morey's DC calculator program. Ken's program number printed number as words 127 became 127 and speak synthesized speech from its input. As Ken said in an interview in 2019, you typed 1 2 plus into DC, which was pipelined to number, which was pipelined to speak, and it said 4 after. It was never good at maths, and it said 4. It was never good at maths. Pipelines are one of the foremost Unix contributions, and obvious only in retrospect, as Dennis said in the evolution of the time sharing system in 1984. The genius of the Unix pipeline is precisely that it is constructed from the very same commands used constantly in simplex fashion. The mental leap in needed to see this possibility and to invent the notion is large indeed. Now, grep. Unix began life as a command line system, that is, one where users type commands to run programs rather than pointing at and clicking icons with a mouse, as is normal when using Windows or Mac OS. A command line interface is not where I lost track. Unix began life as a command line system. Yep. That is one where users type commands to run programs rather than pointing at and clicking icons with a mouse, as is normal when using Windows or Mac OS. A command line interface is not as easy as point and click for novices, but in hands of someone with very moderate experience, it can be far more effective. It allows for automation that is not possible with a graphical interface. Sequences of commands can run from scripts and applied to a larger number of files with a single command. Unix has always had a rich collection of small command line tools, that is, programs that help simple frequent that handle simple frequently occurring tasks. Half a dozen commands manipulate the system, like ls for listing the files in a directory rather like Finder on Mac or Explorer on Windows. Cat and cp copy the file in various ways. Moves for renaming, and remove for removing. There are commands for processing file contents, like wc for counting the number of lines, for counting things, sort for sorting files, plus handful for comparing files. Another few for transformations, like case sensitive, and some for selecting parts of the file. Unix users will recognize unique comp diff or tail. Tail prints the last 5 lines, right? TR and come. Add another dozen tools that don't fit into those categories, and you have a repertoire of 20 or 30 commands that let you do all kinds of basic tasks easily. In effect, the tools are verbs in a language, and files are the nouns that verbs apply to. The language is often irregular, and each command has optional arguments that modify its behavior. For example, sort normally sorts line by line in alphabetical order, but arguments can change it so it sorts in reverse order numerically on specific fields, and so on. To use Unix well, one must learn what amounts to a family of irregular verbs, just as for natural languages. Naturally, there are frequent complaints about the historical irregularities, but occasional attempts to rationalize them have the most part not being very successful. The prototype tool, the command that started us thinking about tools more than just programs, was grep. The pattern searching program originally written by Ken Thompson, as Ken said about it in 2019 interview. I had it written. I had it written, but I didn't put it in the central repository of programs because I didn't want people to think that I uh, dictated what was there. that I dictated what was there. Said Doug McElroy said, "Wouldn't it be great if we could look for things in files?" I said, "Let me think about it overnight." And the next morning, I showed him the program that I had written earlier. He said, "That's exactly what I wanted." Since then, grep has become a noun and a verb. It's even the OED. The hardest part was the mate. It was originally S for search. It's even the OED. What is since OED? Since the OED has blessed grep as a legitimate, it's even in the OED. What the heck? Oxford English Dictionary. Oxford English. And due to some reason, I like have a physical copy of it. Shared. It is shared. The word is in the Oxford English Dictionary. Is this where I have to search? Grep. Shared. It is there. Transitive to grasp or seize firmly or transitive. To search for a string of characters using the grep command. A Unix command used to search files or occurrences of strings or of characters. Yeah, grep is amazing. I have 21 subscribers. That is just crazy. They are going like crazy. Okay, now yeah, after that, the name grep comes from a command in the ed text editor g/r/e that prints all lines that match the regular expression re. Oh, global re print, I guess. Regular expression pattern re. The Oxford Dictionary entry for grep 4.2 has it right. Since the OED has blessed grep as a legitimate English word, I am going to use it without using fonts or capitalization. My personal favorite grep story comes from a day in 1972 when I was called by someone at the labs who said, "I noticed that when I hold my new pocket calculator upside down, some of the numbers make letters. For example, 3 becomes E and 7 becomes L. I know you guys have a dictionary on your computer. Is there a way you can tell me what words I can make on my calculator? What when I hold upside down? That is crazy. Grep string characters. A Unix command used to search file for occurrences. Yes. Being in a research group, it felt good to be able to help someone who had a really practical problem. So I asked him what letters he could make when he hold his calculators upside down, and he said BEHILOS, behilos, behilos. So if you turn that upside down, what do you get? B is 8, I guess. E 3, H is what the heck is H? Mm, There is no. Huh? What letters he could make when he do behilos. Yeah. I turned to my keyboard and typed this command. If any of these letters occur from one or any number of times from start to finish in any string, put there that use that in here. Behilos. Okay, I can do this. This is easy enough. Shit, my head got cut off. Yeah, let me do Behilos. What are the files I have in here? Let's just go to some folder, cd cls. I will use that command on command line arguments dot c. Now grep look for how do I write regular expressions into grep by using single quotes. That's it. inside single quotes, I'll have at the start, I have something like any Bahilos and end till the end, like any one or any occurrences, and do this till the end, right, right. On what file? Do this on command line args, and I have none. Okay, that is crazy. The file, this is the oh, user text. Let's do user text. Grep Bahilos dollar. Where the fuck is there it is? And wait, that is that a or is it a tick? No, that is a single quote. Use this on slash user slash there was there was dict here which is not in my root repository, so let's go to pull use others and nah, it's fine, it's fine, it's fine. This the word list from Webster's second international dictionary with this many words, one per line, and the cryptic string of characters between quotes is regular expression or pattern that in this case specifies the line that contain only arbitrary combinations of any of these seven letters and nothing else. Out came the most amazing list. 263 words in figure 4.4. I am a naive speaker of English, but that list has a fair number of words I have seen. Uh, oh, H. H is for ILOS. Bahilos. Before, in any case, I have printed them out and sent them to the guy. I think he must have been satisfied. I never heard from him again, but he left me with a great story and a wonderful demonstration of the value of tools like grep and notations like regular expressions. Over time, the word grep became a noun, a verb, gerund, grepping, and active noun and part of everyday speech in the Unix community. Have you ever gripped your apartment for your car keys? That is crazy. Bumper stickers and t-shirts riffed on the AT&T commercial that invited people to search out and touch someone, reach out and grip someone, reach out and grip someone. Have you ever gripped your apartment for your car keys? That is crazy. Arno Penzia, the Nobel Prize winner and the vice president of research, my boss, the three levels up, called me one day to ask whether it was safe for him to use this phrase in a public talk. Yep. Well, I don't know. I'm no authority, but yeah, that would be cool and crazy. Regular expressions. I have used the phrase regular expressions without really explaining it. Well, I know a bit. A regular expression is a notation for searching for specifying a pattern of text. It could be as simple as a word like expression or a phrase like regular expression uh, or something significantly more complicated. In effect, a regular expression is a small language for describing text patterns. In usual notation, a word or phrase is a regular expression that stands for itself in the text and here is the list of words which can be written in a calculator upside down. Expression recognizer will find the words wherever it occurs. Regular expression also makes it possible to specify more complicated patterns by giving special meanings to some characters called meta characters. For example, in grep, the meta character dot will match any single character, and the matcher star will match any number of repetitions of the preceding character. So the dot star will match any sequence of characters enclosed in a parentheses. Yes, parentheses are also there. Unix has had a long love affair with regular expressions, which are pervasive in text editors in grep and its derivatives, and in many other languages and tools. Regular expressions of a slightly different flavor are also used in a file name pattern as seen in shell wildcards that match group of files names. Okay, Ken Thompson's QED editor on Multics, and later the GE 635, where I first encountered it using regular expressions. And Ken invented a very fast algorithm that allowed it to process arbitrarily complicated expressions quickly. The algorithm was even patented. QED was sufficiently powerful that in principle it was possible to write any program just using editor commands. It was possible to write any program just using editor commands, though no one on their right mind would do so. I even wrote a tutorial on QED programming that was largely wasteful efforts, but it started me writing such documents. QED was a overkill for most purposes. Uh, Used regular expressions. Okay, a program just uses regular expressions. QED was a overkill for most purposes. The Unix ED text editor that Ken and Dennis wrote originally and several other people subsequently modified, even me, was much simpler than QED, but it too had regular expressions. Since grep was derived from ED, its regular expressions were the same as those in ED. Uh-huh, uh-huh. A variant style of regular expressions is used for file name wildcards. Although wildcards are interpreted by the shell, because primary memory on the P7 was so limited, the first implementation was a separate program called glob for global, called by the shell, and the act of generating an expanded list of file names from a pattern was called globbing. The name glob lives in libraries, even in several programming languages today, including Python. Glob, called glob, okay, and the act of generating an expanded list of file names from a pattern. Ah, finding files using a pattern is cool. One of Al-Aho's early contributions to Unix was an extension of grep that allowed a richer class of regular expressions, for example, making it possible to search for alternatives like this or that. Al called the program egrep for extended grep. It's worth saying a bit more about egrep since the story behind it is an excellent example of the kind of interplay between theory and practice, and of typical interactions among members of 1127 that led so much good software. This story came from Doug McElroy. Whose first egrep was a routine implementation of an algorithm from design and analysis of computer algorithms by Aho, Hopcroft, and Ullman. I promptly used it for a calendar program that used a huge automatically generated regular expressions to recognize date patterns like today, tomorrow, until the next day, business day, and so on, represented in a large range of date styles. Okay, to else chagrin, it took some 30 seconds to compile into a recognizer that would then run in no time at all. He then came up with the brilliant strategy of generating the recognizer lazily as parts of it were needed rather than all in advance. So only a tiny fraction of the exponentially vast number of states were ever constructed. That made a tremendous difference. In practice, egrep always ran faster no matter how complex the pattern it was dealing with. So egrep is distinguished by technical brilliance, invisible unless you know how badly standard methods can perform. Okay, egrep is better. This is a common Unix story, a real problem for a real user, deep knowledge of relevant theory, effective engineering to make the theory work well in practice, and continuous implementation. It all came together because of broad expertise in the group, an open environment, and a culture of experimenting with new ideas. Now, the C programming language. New programming languages have been a big part of Unix since the very beginning. One of the most important contributions of Multics was its attempt to write the operating system in a high-level language, PLI. PLI was created in 1964 by IBM to try to combine all the good ideas from Fortran, COBOL, and Algol into a single language. It turned out to be a grand example of the second system effect. The second system effect. Second system effect sounds cool. Second system effect, okay, is a tendency to over-engineer a system that succeeds a small successful system. It can also. The second system effect can happen when there are inflated explanations and overconfidence. Second system effect. Uh, or second system syndrome is the tendency of small, elegant, and successful systems to be succeeded by over-engineered, bloated systems due to inflated expectations and overconfidence. A simple thing was turned into something much more complicated and over-engineered due to bloated expectations and overconfidence. That is a good enough explanation for now. And yep, second system effect. Language was too big and complicated for most programmers. Ah, It was hard to compile, and a working compiler for Multics was not delivered on time as an interim measure. Doug McElroy and Doug Eastwood, two Dougs, created a simplified subset called EPL, early PLI, for use with Multics, but it was still a complicated language. BLPL, BCPL, Basic Combined Programming Language, was another language intended for system programming. It had been designed by Martin Richards, a professor at the University of Cambridge, and he wrote a compiler for it while visiting MIT in 1967. BCPL was much simpler than any dialect of PLI and was well suited for writing operating system code. Members of the Bell Labs Multics effort were very familiar with BCPL. When the labs pulled out of Multics, Ken Thompson decided that no computer is complete without Fortran. So he started to write a Fortran compiler for the PDP-7. This proved too tough since PDP-7 Unix had only 4K 18-bit words, 8 KB for 4,000, for user programs like a compiler. Ken kept redesigning, eventually coming up with a language that did fit the PDP-7 and was much closer to BCPL than Fortran. He called it P, as Dennis Ritchie explained in the development of the C language in 1993. B can be thought of as C without types, and more accurately, it is BCPL squeezed into 8 bytes of memory and filtered through Thomson's brain. Its name most probably represents a contraction of BCPL, though an alternate theory holds that it derived from Bon, an unrelated language created by Thomson during the Multics day. Bon, in turn, was named either after his wife Bonnie or, according to an encyclopedia quotation in its manual, after a religion whose rituals involved the murmuring of magical formulas. So the C language has the name C because there are two theories. Well, the obvious thing is that there was a language called B, which was created by Ken Thompson, and after B, Dennis Ritchie created the C programming language, which is like a natural progression after B you get to C. And now the question, there are two theories why B was called B. Why was it named B? First, it is that he wanted to implement the BCPL language and could not do so in the computer that it had. The computer that Ken Thompson had, it had only 8 kilobytes of memory. So he, instead of creating a whole compiler for the BCPL, he created a subset of the language called B, right? That might be one reason why it is named B, or another reason that it is named its name derives from the Bon programming language, which Ken Thompson created in his Multics days, and he named that language Bon, maybe because of his wife Bonnie, which seems like a viable reason. And I guess it is the B from BCPL. Up to this point, the computers in our story have been word oriented, not byte oriented. That is, they manipulate information in chunks that are significantly larger than a single byte. The IBM 1790 and its similar computers, like the GE series, manipulated information naturally only in chunks that were 36 bits, roughly 4 bytes. Why roughly? That is right. Yeah, 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 4.5 bytes. PDP 7 chunks were 18 bits, 2 bytes, oriented, roughly 2 bytes. Word oriented computers were clumsy for processing bytes individually or in sequence. Programmers had to use library functions or go through programming contortions to access the individual bytes that were packed into the larger chunks. By contrast, the PDB-11 was byte-oriented. Its fundamental unit of primary memory was 8-bit byte, not 18 or 36 words of earlier computers, though it could also manipulate information in larger chunks like 16 and 32-bit integers and 16-bit addresses. Yep, P was a good fit for word-oriented computers like PDB-7, but not for byte-oriented computers like PDB-11. So when PDB-11 arrived, Dennis started to enhance B for the new architecture and to write a compiler for it. The new language was named NB for Newbie, and eventually it became C. One of the main differences between that were B was typeless. C supported data types that matched the data types that the PDB-11 provided, a single byte, two-byte integer, eventually floating point numbers with 4 or 8 bytes, and were languages like BCPL and B treated pointers, memory addresses, and integers as the same. Pointers and integers as the same. C formally separated them through, though for many years programmers unwisely treated them as if they were the same size. Now, well, are they the same size? I don't know. I don't know about the size. Let me see. Ah, shit, my screen has been stuck for some while. That is just very stupid. Let me get it running again. And here we are. You can see my face and you can see my screen. Now I want to write a program to see the size of word. Yes, I will have to compile the file. Yep. Let's do size of the the n size of pointers.c include stdio.h main printf size of pointer percent %d new line and size of okay, let me do int pointer a gets the address of one that can do up int a equals one. This becomes a, this becomes b, and this becomes b int, but they are oh, or maybe I can just do a but get the address a- address of a. Format specifies type int, but the argument has type unsigned long. Then just do that unsigned long alex. Wait, what? No, yeah, clang size of pointers. Send the output to pass that out. 8 bytes. Unsigned long. Okay, it is 8 bytes long. That is 64 bits. One of C's novel contributions to programming languages was the way that it supported arithmetic operations on typed pointers. A pointer is a value corresponding to an address that is a location in primary memory, and it has a type, the type of the object that it will point to. If that location correctly responds to an element of array of that particular object, then in C adding 1 to the pointer yields the address of the next element of the array. Although careless use of pointers is a recipe for broken code, pointer arithmetic is natural and works when used correctly. It has been clear for some time that Unix should be converted from assembly language to a higher level language, and C was the obvious choice. Ken tried 3 times in 1973 to write the kernel in C, but it proved too difficult unless Dennis added a mechanism for defining and processing in nested data struct to the language. At that point, C was sufficiently expressive for writing operating system code, and Unix became mostly a C program. The 6th edition kernel has about 9,000 lines of C and about 700 lines of assembly code for machine-specific operations like setting up registers, devices, and memory mapping. Yep. The first widely distributed description of C was the C programming language, a book that Dennis and I published in 1978. A second edition was published in 1998. Yay, KNR. I had learned B rather superficially, and for my own amusement wrote a tutorial to help others to learn it too. When Dennis created C, it was easy to modify the B tutorial to make one for C. The C tutorial provided to be a popular, and as Unix and C spread through, I thought that it would be worth trying to write a book about C. Naturally, I asked Dennis if he would write it with me. He might have initially been reluctant, but I twisted his arm harder and eventually he agreed. Getting Dennis to work on the book was the smartest, or maybe just the luckiest thing I ever did in my technical career. It made the book authoritative because Dennis was a co-author and it allowed me to include his reference manual. I wrote the first drafts of most of the tutorial material originally, but Dennis wrote the chapter on system calls, and of course provided the reference manual. We made many alternated passes over the main text so that a blend of our styles, but the reference manual stayed almost exactly as it had been, a pure example of Dennis's writing. It describes the language with what Bill Plager once called spine tingling precision. The reference manual is like C itself, precise, elegant, and compact. Hmm, let's see the C reference manual. Emmanuel, the GNU C reference manual, or lexical elements, and there is quite a bit of stuff. This is actually not too big. Data types, enumerators. Okay, that is actually not too big. That is fine. Yeah, and the first official standard from NC, the American National Standard Institute, and also from ISO International Standards Organization, was completed in 1989. It's a description of the language. So in 1989, the first mm, the first standard was completed for the C programming language by NC and ISO, NC Indian, not Indian, American National Standards Institute, American National Standards Institute, and from ISO, International Standard Organization, was created in 1989. 1989, okay. What happened in 1989? Okay, that happened. Okay, the standard was created in 1989. That's it. The description of the language was directly based on Dennis's reference manual. Dennis was involved in the early stages of the first C standard where his standing as the creator of the language gave his opinion weight, and he was able to head off one or two really bad proposals. The C language is important, but also cover of K in our first edition. The C language is important, but so also is its use of standard library that provides the basic facilities that programmers need for operations like formatting input and output. For formatting input and output, string processing, and mathematical functions, C came with a modest sized library of functions so that programmers did not need to reinvent each routine when they wrote a new program. Yep, the largest library component provided formatted outputs, familiar today to all formatted outputs to all programmers through C's printf function, which has been adopted in many other languages. Mike Lensk's portable I/O package, written in 1972, so that the programmers could be easily moved to and from UNIX, contained the first version of printf and also included scanf for parsing formatted input. There were these were reworked and included with the C compiler, although printf and scanf have had extensions since the core set of conversations work as they did in the early 1970s, as do most of the other functions in the library. Today, the standard library is just as much part of the C standard as is the language specification itself. Well, the standard library has been specified in the standard, right? Today, the standard library is just as much part of the C standard as is the language specification itself. It is interesting to contrast C approach to other languages in Fortran and Pascal. For example, input and output are parts of the language with a special syntax for reading and writing data. Some other languages don't include input and output, and at the same time don't provide a standard library, which is probably the least satisfactory choice. C has been very successful, one of the most widely used languages of all time. Although it began life on PDP-11 Unix, it has spread to essentially every kind of computer that exists. As Dennis said in a paper for the Second History of Programming Languages conference in 1993, C is quirky, flawed, and an enormous success. While accidents of history surely helped, it evidently satisfied a need for a system implementation language efficient enough to displace assembly language, yet sufficiently abstract and fluent to describe algorithms and interactions in a wide variety of environments. Yep. Of course, there are many programming languages, often with noisy adherents and detractors, and C comes in for its share of criticism. It remains the gold language of computing, however, and is almost always in the top two or three in lists of language popularity, influence, and importance. To my mind, no other language has ever achieved the same balance of elegance, expressiveness, efficiency, and simplicity. C has also inspired the basic syntax of many other languages, including C, of course, C++, Java, JavaScript, Awk, and Go. It has been an exceptionally influential contribution. Software tools and RET4. Okay. By mid to late 1975 was the year David Goggins was born. Unix had been publicly described at conferences and in journal papers, and the sixth edition was in use to attempt a hundred and was in use at perhaps 100 universities and was a limited number of commercial or operations, but most of the technical world still used Fortran and ran on operating systems from the hardware vendors like IBM's System 360. Locally, most programmers at Murray Hill used the GE 635 with GE's batch operating system, Gisco, renamed GECOS, when GE sold its computer system to Honeywell in 1970. By 1973, I had started to program in C regularly, but I was still writing Fortran as well. Although Fortran was fine and numerical computation numerical computation, its control flow statements were almost non-existent, and it was constrained by its origin as a punch card based language from the 1950s. By contrast, C control flowed naturally, so to speak. Accordingly, I wrote a simple compiler that would translate a dialect of Fortran like C that looked like C into valid Fortran. I called it RAT4 for Rational Fortran. RAT4 converted C control flow with if-else for while and braces for grouping into Fortran's if and go-to statements, and its one opening loop construct to the do loop. The preprocessor also provided notation conveniences like free-form input, and not the rigidly formatted 80-column card images that Fortran is still required. A convenient comment convention and natural, logical, and relational operators like these instead of Fortran's clunky .lt larger than and dot ge dot greater than or equal to. As a short example, here is a Fortran program of chapter 1 in one of the several ways that might be written for RAT4. Make V an identity matrix. Do I equals this to this if this equals this, then do this, else do this. Okay, a RAT4 was the first example of a language that based its syntax on C. Writing Fortran in RAT4 was if I do say so myself, infinitely more pleasant than writing standard Fortran. Radford didn't change Fortran semantics or data types. It had no features for processing characters, for instance, but for anything where Fortran would be a good choice, Radford made it better. Free form input and C like control where control flow made it feel almost like writing in C. A tour the force of both theory and practice. Brenda Baker created a program called Struct that translated arbitrary Fortran programs into RAD4. That is just opposite of what he did. Brenda showed that almost any Fortran program has a well-structured form. There is essentially a unique best way to render it in RAD4. People who used Struct found that RAD4 version was almost always clearer than the Fortran they had originally written. Bill Flower and I decided to write a book to evangelize the Unix tools philosophy for a wider audience and programmers who were writing Fortran on non-Unix systems. Software Tools, which was published in 1976, represented RAD4 versions of standard Unix tools like file comparison, word counting, grep, and editor like ed, uh, roof-like text formatter, and a RAD4 preprocessor in itself, all written in RAD4. And yep, our timing was about right. The book sold moderately well, and a software tool user group sprung up, spearheaded by Debbie Scherer, Dennis Hall, and Joe Swintek at Lawrence Livermore Labs. They polished and refined the programs, added new tools of their own, made distributions of the code, organized conferences, and kept everything running smoothly for years. Their code was ported to more than 50 operating systems, and the user group remained active and influential until it demolished the late 1980s. In 1991, Bill and I published a version of the tools book based on Pascal, which at the time was popular as a teaching language in universities. Pascal had good properties, including sensible control flow and recursion, both of which were missing from Fortran. Unfortunately, it also had some not so good properties like awkward input and output and almost unusable character strings, which I described in a paper titled Why Pascal is Not My Favorite Programming Language. I submitted the paper to a journal, but it was rejected as too controversial or perhaps not substantial enough. It never was published, but in spite of that, it is cited surprisingly often. In any case, as C and Unix became more widely available, Pascal's serious limitations made it less and less popular. So, software tools in Pascal was not widely read. In hindsight, a C version would have had far more impact both in the short term and in long term. In hindsight, a C version would have had far more impact both in short term and long term. Biography Doug McElroy. Rob Pike has called Doug McElroy the unsung hero of Unix, and I agree. Ken Thompson says that Doug is smarter than everyone else, which also seems accurate, though Doug himself says, I will leave to others to assess how smart I may be, but I know that many of BTL's practicing machines mathematicians were much smarter. Suffice it to say that there were many. Wait, why is wait? And that is fine. That is fine. hmm Suffice it to say that there were many outstanding peoples at the Bell Labs. The imposter syndrome was not unknown, and one was continuously stretched trying to keep up, no matter who is right here. Unix might not have existed and certainly would not have been as successful without Doug's good taste and sound judgment of both technical matters and people. Doug received his undergraduate degree in physics, from Cornell in 1954 and his PhD in applied mathematics from MIT in 1954. In 1959, he too worked for a summer at Bell Labs and joined permanently in 1958 and became head of the computing techniques research department in 1965, 2 years before I first met him. As described earlier, I spent the summer of 1967 as an intern in Doug's department, nominally working on a storage allocator problem that he suggested, but in fact doing my own thing. One of his many good qualities as a manager was that he wasn't bothered by that at all. I have already mentioned Doug's early language work on PL and EPL. Once Unix was underway, he wrote a wide variety of fundamental software. His storage allocator malloc was used for many years. It is still used, and his research on allocators affected subsequent work. He also wrote a bunch of commands. The list on his web page at Dart Mount includes spell, diff sort, join, graph, speak, tsort, calendar. Hey, what speak? What is speak? Well, it does not exist here. In ZSH, it does not exist. Oh, he was born in 1932. I have seen him somewhere. I have seen him somewhere. Doug McElroy. And he is still alive and kicking 1932. Okay, that is. He is older than Al Pacino and Bob De Niro. He. Wait, 1932. That means that he is older than Mikhail Tal and Bobby Fischer. And he might be older than Stanley Kubrick. I guess Stanley Kubrick was born in 1930s or 27, 28. Okay, okay. Well, he's not older than Kubrick. Kubrick is a bit old. Charlie Munger was pretty old. Charlie Munger was pretty old. 1924. He died at the age of 20, 99. That is just crazy. And he has written quite a few books. Not quite a few on success. Only two books. That is okay. And who was his friend? Charlie Munger, of course. How can I have Warren Buffett? Warren Buffett, and he must have written quite a few books. Yeah, he has fucking written quite a few books. That is crazy. Well, back to the topic, back to the thing. Yep, some of these are small, like Echo, while some are large, like sort and diff, but most are central to Unix computing, and many are used to this day. Of course, pipes were his idea too, though the final version used Ken's syntax, and their existence was due to Doug's ongoing lobbying for such a mechanism. His version of spell made effective use of dictionary and heuristics for identifying parts of speech to find potential spelling mistakes using only mere song resources. Doug's version of diff implements an efficient algorithm invented independently by Harold Stone and Tom Smith, Shi- Si- Szymanski, Tom Szymanski, for comparing two text files, finding a minimal sequence of changes that will one into the other. That will convert one into the other. This code is at the heart of source code control system that manage multiple versions of files like Git. Such systems of no Git does not store the differences; it stores the files themselves. and finds the SHA-256 for them. Such systems most often work by storing one version and a set of diffs, generating other versions by running diff algorithm. This is also used in the patch mechanism that's used for updating programs rather than sending new versions of programs to someone. Send a sequence of ed text commands computed by diff that will convert the old version into the new. Yeah, yep. And then, yep, here the diff program is another example of how good theory can be combined with good practice engineering to make a fundamental tool. The output that diff produces, quite early in Unix days, 1127 brought a novel device, a Vortex voice synthesizer that converted phonemes into sound. Doug created a set of rules for converting arbitrary English text into phonemes, phonemes and wrote a program called Speak that used the rules to generate Vortex input. Okay, English spelling is of course notoriously irregular, so no set of rules can do a perfect job. The output of Speak was often imperfect, sometimes funny. My name rhymed Brian Kernighan and almost always accurate enough to be genuinely useful. The program was just another command, so it could be used by anyone without pre-arrangement. Text sent to speak was played through a loudspeaker in the Unix room. This led to any number of odd services. For instance, every day at 1 p.m. the vortex would say lunchtime, yummy, 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 as a reminder to the inhabitants that it was time to head off to the cafeteria before it closed in 1:15. Wait, if it closes in 1:15, so will they just complete eating their food in 15 minutes? That is crazy work ethic, I would say. There is also a service that monitored incoming telephone lines, and when one rang silently, would announce phone call for Doug, or whoever in a shared space. It was much less distracting than frequently ringing phones. Doug's interest was broad and deep. Among other things, he was an expert in map projections, which are a specialized form of mathematics. His map program provided several dozen projections, and to this day, he is still producing new ones that show up in Christmas cards sent to friends and so on his Dartmouth web page. This is map. Oh, the way you can project a map. Mhm, mhm. Doug was a superb was a superb technical critic, often the first person to try out some new program or idea. He would experiment at the earliest possible time, and since he had excellent taste, his opinions on what was good and what needed to be fixed was invaluable. There was a steady flow of people to his office to get advice and critical comments on ideas, algorithms, programs, documents, pretty much anything. Bjorn Strausstrup, Bjorn Strausstrup used to drop in on me to discuss C++ and explain some new ideas, then move a few doors along the corridor to Duck's office to get some serious feedback on the language design. Dennis Ritchie and Doug McElroy, 2011. Doug was usually the first person to read drafts of papers or manuals where he would deftly puncture rhetorical balloons, cut flappy prose, and weed out unnecessary adverbs, and generally clean up the mess. In Mike Mahoney's Oral History of Unix, 1989, El Ahu says of Doug, he understood everything that I was working on with just the most fragmentary descriptions, and he essentially taught me to write too. I think he is one of the finest technical writers that I know of. He has a flair for language and a flair for economy of expressions that is remarkable. Economy of expressions. Doug was the outside reader on my thesis, where he greatly improved the organization and exposition. He also read multiple drafts of all the books that I co-authored with others at the labs, always making them better. He refined and polished the manual pages for commands, and he pulled together and organized the contents of the manuals for the 8th through 10th editions of Unix. He did all of this with enthusiasm and care at some cost of his own research. Doug stepped down from the management role in 1986 and retired from the Bell Labs in 1997, headed off to teach at Dartmouth. Figure 4.7 is a picture taken at Bell Labs in Murray Hill during 2011 celebration of the Japan Prize awarded to Ken and Dennis. A Japan Prize was awarded to Ken and Dennis, and this is Doug McCullough and Dennis Ritchie. And that is it for today's stream. That was cool, 1 hour stream, and yep, that is it for today. Thank you.